All right. Listen up, please. So, for the rest of the year, we basically have 2 more things that we need to learn, okay? One of them is today. Hopefully we'll get through it all today. I think we will. And then one of them will be probably either Friday or the beginning of next week, okay? And then we're done with new stuff, and then we'll just be doing some labs to kind of reinforce that stuff, okay? So what we need to learn today is the difference between a strong acid and a weak acid, and the difference between a strong acid and or strong base and a weak base, okay? Which can be kind of an important distinction so that you don't, put your hand into something that will melt your skin off. So that's what we're going to talk about here, okay? Now, there are 7 strong acids. Do you guys have this on your notes already?
Yeah.
Okay. So there's your list. You need to know those 7. Yeah. But it's not that hard. Here, let me show you something. Well, it's kind of hard. But let me show you something that will help you with 3 of them. 3 of them are in the same column on the periodic table. You've got chlorine, bromine, and iodine. Okay, HCl, HBr, HI are all strong acids. Now, where that's going to mess you up a little bit is you're going to think HF is a strong acid too, especially since I don't know if you've ever heard of hydrofluoric acid before. Have you heard of hydrofluoric acid? It's nasty, nasty stuff, okay? It will actually eat through glass, so you can't keep it in a glass container. It is sometimes used in television shows to dispose of people. So, I mean, don't do that. I don't even have any hydrofluoric acid in here, so you couldn't anyway, all right? But it's very nasty stuff. So why is that not a strong acid? Because that seems pretty strong to me, right, if it will eat through glass? Okay, well, it turns out that's not what strong and weak actually means. It doesn't mean how reactive is it. It means something different. So we'll get to that in a minute, okay? But HCl, HBr, HI, those should be pretty easy to remember. If you start with hydrochloric and go down, those next 3 are all strong acids, okay? A couple of these you know. Hydrochloric, oh, there it is. Well, we know hydrochloric acid, okay? We know that one's strong. Nitric acid, HNO3, that's the stuff that I put on the penny at the beginning of the year. Makes sense that that's strong, right? Okay. Sulfuric acid, anyone ever heard of sulfuric? Yeah, that's really nasty stuff, okay? If I had to choose which one of these not to get on my skin, that would be the one right there.
Do you have that?
We do have some of that.
Wow.
Well, sometimes we use it for labs. Yeah. I don't think we've ever used it in this class. I don't think we've used sulfuric this year. We use it for AP sometimes. What else? Okay, these 2 in the middle, these might be the hardest ones, the chloric acid and the perchloric acid. I'm not sure that you would come up with those off the top of your head, but you need to know this list. And the reason why is because if you know what the strong acids are, then you know every other acid is weak. All right? Those are the only 7 that we would classify as strong. Now, I say those are the only 7 we classify as strong. I'm talking about naturally occurring acids. There are acids that can be manufactured in laboratories that are much stronger than any of these, okay? But I'm not talking about those. All right? So there's your 7 strong acids. You might put a star by that just to remind yourself, hey, I need to know these. I need to memorize these. All right? These substances will completely ionize when they're dissolved in solution, okay? What does that mean, completely ionize? Say it again. Yeah, break apart, basically. Split apart into ions, okay? So a strong acid, you put HCl into a solution, it's going to completely break apart, okay? So in other words, if I have 1 mole of hydrochloric acid, HCl, and I put it into a solution, then I'm going to end up with 1 mole of H plus and 1 mole of Cl minus. Okay, it's going to completely split apart. All right, all the HCl you put in there breaks. Does that make sense? Okay, that's a strong acid. Reaction only goes in one direction. Once it breaks apart, it does not come back together. Okay, so you put HCl into solution. There is no HCl in there anymore. It's only H plus and Cl minus running around in that water. okay? That's what makes it so acidic, because it's this H plus right here. That's what really messes with you, or messes with, eats things. Because this H plus is really reactive, okay? Kind of unstable. So it'll go after stuff and try to steal electrons from other things. Okay, so write the ionization reaction for hydrochloric acid. So the way that you would write this as a reaction, I'm going to write it up here. You would write HCl goes to H plus plus Cl minus. Okay? And I'm not super worried about states of matter here. If you want to put aqueous and aqueous here, this happens in solution. So when you put it into water, this is what happens. So technically these are all aqueous. Okay? But you don't have to put the states of matter. But that's all you have to do to write the ionization reaction for hydrochloric acid. Okay? That's pretty easy, right? Okay. Weak acids. This is a little bit trickier, okay? So if it's a weak acid, it does not completely ionize. It doesn't completely break apart. All right? So what that means is some of, let's say that I have, to use an example here, so I've got some acetic acid, C2H3O2. Why did I pick that one? I'm going to do HF, because that's faster to write. Okay, so I dump a bunch of HF molecules into water, okay? Most of them will just stay together, but every once in a while, one of them will split apart into H plus and F minus, okay? So it doesn't completely ionize. That means only some of the molecules break apart. Most of them stay together. Does that make sense? Okay, so that's the difference between a weak acid and a strong acid. So the reason hydrofluoric acid, in case you're curious, the reason that it will eat through glass and anything living, basically, is because of the F minus, not so much because of the H plus. Okay? So that F minus in there is really, really, really reactive, and it just will destroy lots of things. Okay? Both species are present and are represented in the reaction with an equilibrium symbol. I don't think we've talked about equilibrium at all this year, have we? Well, you know what? We did talk about it a little bit with solutions, with saturated solutions. You guys remember that? So you've got a solid sitting at the bottom. Remember, some of that solid is dissolving at the same rate that some of the stuff that's in the solution is turning back into a solid. Okay? That's equilibrium. Okay? So it's going in both directions at the same time, at the same speed. Okay? So the way that we represent that is with an equilibrium symbol, which looks like this. It's a half arrow going in one direction and another half arrow going back in the other direction. Okay, so that's an equilibrium arrow. We're not going to talk much about equilibrium other than just right here. Okay, in AP chemistry, if you're going on to that, you will talk about equilibrium a lot. Okay, I said that a lot, not I wasn't saying all one word. I told you guys about the a lot. I don't think I have. Okay. Yeah, it's not me necessarily, but I'll explain that to you later when I'm not recording a video. But yeah, anyway, I said it as two separate words, just in case you're curious. All right. Weak acids is any other acid besides the strong. That's why I said you need to memorize the 7 strong acids. Anything that's not on that list that you memorized is weak. Okay? So an example here, write the reaction equation for the dissociation of acetic acid. This is not much different. Okay? So acetic acid, do we remember what the formula for acetic acid is? Yeah, we got to remember what acetate is first, right? Because since it doesn't have hydro in front of it, this is going to be a polyatomic ion, right? Acetate is C2H3O2 1-, if that helps out at all. Okay? So then acetic acid would be this with the hydrogen in front of it, right? So HC2H3O2. And some of that is going to dissociate into H plus and C2H3O2 minus, but not all of it. Well, how do I show that? How would I show that only some of it splits apart or dissociates? The answer is on the board. Yeah, it's with the equilibrium arrow, right? So we just draw an equilibrium arrow here. And what that tells someone who understands the lingo here is it basically tells them, okay, yes, this is happening a little bit, but so is this, right? It can go back in the other direction. And most of the time for a weak acid, there's a lot more of this than there is of the products, okay? Because most of it does not split apart. But that's how we write it. Does that make sense? So the only difference between writing an equation for a strong acid versus a weak acid is to put the equilibrium arrows for the weak acid. And that shows that it can go in both directions. Okay, everybody tracking with me there? Okay. All right, so now let's talk about the difference between monoprotic and polyprotic. This, I will tell you, this is probably not going to be on the exam, but I'm just going to mention it. Monoprotic versus polyprotic. Well, what do you think that maybe means, monoprotic? One of something, right? Okay. Now, what it means one of is 1H plus. In chemistry, because I guess we like to have many terms for the same thing, H plus is also called just a proton sometimes, because that's basically what it is. If you think about it, hydrogen normally has 1 electron, 1 proton, right? Everybody see that up there? 1 electron. Well, I don't know if you can see it up there or not. It has an atomic number of 1, right? Which means that there's basically just 1 proton, okay? We also know hydrogen normally has 1 electron. Well, if it loses that 1 electron to become H plus, now it's just a proton, okay? So that's all H plus is. It's just a proton that's looking for an electron, right? So that's why we call it protic, okay? Monoprotic just means there's just 1 hydrogen there, okay? So acids that produce 1 H plus ion. Give me an example of a monoprotic acid. Hydrochloric, right? Just HCl. There's only 1 H plus there, right? Okay. So then polyprotic, you can also call it diprotic, triprotic, depending on how many hydrogens there are. Give me an example of a diprotic acid. Well, H2O is a little different. We're going to talk about H2O in a minute here, okay? Give me another example, maybe. Say it again. Sulfuric acid, right? H2SO4 is diprotic. You guys see it? There's 2 hydrogens there, okay? Give me an example of a triprotic. You may not be able to pull this one out of thin air. Say it again. No? Phosphoric acid, okay? Phosphoric is H3PO4, okay? So that's a triprotic. Well, because there's 3 hydrogens, right? See how it works? 1 hydrogen, it's monoprotic. 2 hydrogens, diprotic. 3 hydrogens, triprotic, okay? So that's the only distinction there. So this acid, HCl, only gives away 1 hydrogen, okay? This H2SO4 can give away 2 hydrogens, and the H3PO4 can give away 3 hydrogens, okay? Now, it's important that you understand, just because this can give away 3 hydrogens, that doesn't mean it's a strong acid, because it's not on your strong acid list, right? It's not a strong acid because not even the first hydrogen comes off all the time. But there are 3 hydrogens there that can be given away by the H3PO4, okay? All right, so that's monoprotic, whoops, versus polyprotic, okay? Any polyprotic is going to produce more than 1 H plus ion. So there you go, HCl versus H3PO4. Question? I don't know if I'm supposed to, oh, there we go, there's the question. How can you tell if something will be an acid and if it will be monoprotic or polyprotic? Well, we just kind of talked about that, right? But let's talk about it again. How can you tell, first of all, something's going to be an acid? Starts with an H, right? Simple as that. Starts with an H. In this class, it's probably going to be an acid, right? If it's monoprotic, then how many H's would it start with? 1. If it's polyprotic, how many H's would it start with? More than 1, 2 or more, right? It's pretty simple. HS, acid? Yeah, well, we've been talking about that one. So, monoprotic or polyprotic? Mono. Benzene, C6H6. Is that an acid? Probably not. It doesn't start with an H, right? The convention is we start the formula with an H if it's an acid. Okay, that does have some hydrogen in it, but it's not at the beginning of the formula. All right? Phosphoric, we just talked about, so I don't know if we really need to go over that. We wouldn't call it polyprotic because it's not even an acid, right? So only acids get classified as mono or polyprotic, okay? So then phosphoric, we already talked about. That's obviously an acid because it starts with H, and it's polyprotic, okay? You guys getting the hang of that? Yeah. Okay, anhydrides, again, not something that's a big deal, but there are certain things that can become acids or bases when you add them into water, okay? Just kind of depending, and again, you talk about this a lot in AP chemistry. I don't care if you can, I'm not going to give you a question where I say, here's a compound, if you put it in the water, does it make it acidic or basic? Because that's a little more complicated of a question. But there are certain things that can become acids and bases when you add them into water. CO2 is an example of that. Anyone want to take a guess what CO2 does when you add it to water? Does it make it more acidic or more basic? What is our prime example, in order to answer this question, what's our prime example of carbon dioxide being dissolved in water? Soda, right? Is soda acidic or basic? It's acidic. And actually, it's not, this isn't where all the acidity comes from, but it is acidic because of the carbon dioxide that's dissolved in there, okay? If you got something like Sprite or 7-Up, there's also going to be citric acid in the Sprite or 7-Up, and that citric acid will also cause it to be more acidic, okay? But in most sodas, it's the carbon dioxide that makes it acidic, all right? So you put CO2 into water, it makes it an acid, okay? H2O is, when you add H2O to water, it doesn't make it more acidic or basic. But I'm going to take this opportunity here to talk about H2O. Because someone yesterday, I think it was Kelsey, made the observation that water can also be, the formula for water can be written like that, which is kind of interesting. Because do I classify that as an acid because it's got an H in the front of it? Or do I classify it as a base because it has OH at the end? The answer is yes. You can classify it as either one, okay? Because depending on the situation, it can act like an acid or it can act like a base, all right? So that's, again, that's more for AP chemistry than here. I'm just telling that to you and because I know some of you are planning on going on to AP chemistry. Yeah. All right. Then you got something like, oh, I get it. Okay, well, I took that opportunity to tell you about H2O, but what they were saying was carbon dioxide added to water, okay? It wasn't saying and H2O was something that becomes acidic or basic. Okay, calcium oxide, when you put that into water, this one you wouldn't, there's no way that you would know this, but I'm just going to show this to you right now, okay? So if you put calcium oxide into water, any guesses what happens to it? Yeah, usually when you put ionic compounds into water, they break apart, right? So this one's going to break apart into Ca2 plus and O2 minus, okay? Calcium in water doesn't really do much. Oxygen, when you put oxygen O2 minus into water like this, it's not very happy, okay? This O2 minus, not very stable. It's going to try and grab hydrogens from wherever it can, okay? If you put O2 minus, whoops, and again, I'm just telling you this for the fun of it, because this is fun, right? So you put O2 minus into water, it's actually going to steal a hydrogen away from that water. Okay, and when it does that, it becomes OH minus plus OH minus, right? Does that make sense? Because now the oxygen has a hydrogen, and we took a hydrogen away from the water, so now they're both OH minus at that point. Well, if you've got a bunch of OH minus now in the solution, then what is this? It's a basic solution. It's very basic, right? Because we're making a bunch of OH minus. So you put something like calcium oxide into water, you're going to make it basic, okay? And again, that's not something you really need to be able to predict, but I'm just showing it to you, okay? All right, so now let's talk about bases a little bit. Strong bases, when you have a group 1 or group 2 metal combines with an OH minus ion. When I say group 1, what am I talking about? The first column on the periodic table, right? I don't think you were talking about what we were talking about, were you? Okay. So over here, first column on the periodic table, lithium, sodium, potassium, all the way down. If any of those combine with OH, when you put those into water, they're going to be very basic, okay? Same thing with group 2, except for magnesium and beryllium, okay? The first two, and again, you're just going to have to kind of remember that. But calcium, strontium, barium, and radium, if we ever did reactions with radium, since it's radioactive, that's a little awkward to use for normal base reactions. We don't really have any radium in here. But the calcium, strontium, barium, when they're combined with hydroxides, then you put that into water, it's going to give those hydroxides to the solution, makes it more basic, right? Now, weak bases are a little bit trickier, okay? Any other base besides a strong base is going to technically be a weak base. What's hard about weak bases is identifying them, because they don't always have OH in them, right? Like the example I just gave you, O2 minus, that's not an OH, but when you put it in water, it makes OH minus, right? Same thing with this one you probably need to know. So I would write this next to the weak bases. NH3, ammonia. All right, you guys are going to have to move again. Sorry. One of you move. I don't care who. One of you has to move. Yeah, that's not going to help. Well, kid, no. He was pointing to the seat next to him, and I said that's not going to help.
Oh.
I'm waiting. This is really awkward on the video, too. Thank you. I appreciate that. I feel like the bigger man would be able to pick up his backpack a little bit easier than that. All right. So, weak bases, NH3, right? That's a good example of a weak base. What this does when you add it to water is it takes the hydrogen away from water, okay? So it becomes, now because it's a weak base, I'm writing the equilibrium thing. And again, you don't have to be able to write these reactions necessarily yet, okay? But that's what it's going to do. Does that make sense? Because it's taking a hydrogen away from water, so now it's NH4+, plus, and it made OH minus, so that's why it's basic, okay? But because it's a weak base, this doesn't always happen. Not every NH3 takes a hydrogen away from water, just like with the weak acids. So we write the equilibrium arrows to show that it's not always occurring. All right? Sample test questions. Whoops. Yes. I think probably, oh shoot. Tomorrow I was going to do the lab. Okay, so here's the deal. I will give you the practice sheet tomorrow because we're going to, we won't take the quiz on this until Friday, okay, because we're going to do a lab tomorrow. So tomorrow we'll finish these notes very quickly. We'll do the lab. I'll give you the practice sheet, and then we'll take the quiz on Friday, okay? We're pretty much done. We've got 3 minutes left, so we'll call it quits for the day.